Hi, welcome to my YouTube channel. I'm called Peter, and I'll be talking today on assignment problems. We're going to look at what assignment problems are, the different methods for solving assignment problems, and some examples demonstrated using these assignment problems. So let's get on with it, starting with the definition. An assignment problem. The assignment problem is a fundamental combinatorial optimization problem in operation research. Its objective is to find a one-to-one match between a set of resources such as workers, machines, and a set of tasks such as job projects in a way that it minimizes the total cost or maximizes the total profit or minimizes the total time. There are some key characteristics of these assignment problems. You have a specialized transportation problem, which is a specific type of linear programming where the supply of each resource and the demand of each task are exactly one. You have the balance and unbalanced problem, where the balance problem has to deal with if the number of agents are equal to the number of tasks to be assigned to each of those agents. And if unbalanced, which is that either the number of agents is not equal to the number of tasks or the number of tasks are not equal to the number of agents, we call that unbalanced. Now, in such a case, we add dummy rows or columns to the matrix that will be developed with zero cost on them before we start solving the problem. We have matrix representation, which is the cost or time or profit, which will represent and the values will represent them and are typically displayed in an n by n matrix, meaning that it's a square matrix because the number of columns will equal the number of rows. Now we have four different methods for solving assignment problems, namely the enumeration method, the transportation method, the simplex method, and the Hungarian method. Our class of today is going to emphasize on the enumeration method and the Hungarian method. Let's start first with the enumeration method. Now, in this method, all the possible permutations of the various tasks and resources from the given problem are being computed, meaning that, for example, if you have three jobs or tasks to be assigned to three persons or workers, the number of possible cases or combinations that you have will be simply 3 permutation 3, giving us 6 different cases or combinations to have these different workers or persons assigned jobs. The total time or cost for performing all the designed given tasks from the problem is calculated, and the optimal assignment of the job or task is obtained by identifying the optimal value from the total cost or time. That is, the sum of all the different costs for the different combinations or the different assignments that we're going to different permutation assignments that we're going to have will be summed up and will have a certain value. Now that with the smallest value will be our optimal assignment. The enumeration method has a time complexity of big O n factorial to the time by n. Why? Because where our n is simply the number of the agents and tasks, and it is the agent. It is because the agent or every agent must be assigned exactly one task, and this method calculates the cost for all possible permutation. Now, this method is highly inefficient and suffers from combinatorial explosion for larger matrices, making it impractical for most real-world scenarios. That is, the greater the number of agents and jobs to be assigned to them, the harder it will be for us to use this method. Now, next we have the algorithm that we are going to follow to use this method. First is that we need to check if the matrix developed is a square matrix, meaning the number of rows and the number of columns are equal. let's say we have a matrix called M, and this matrix has n number of rows and n number of or m number of agents. We check if the number of rows and the number of columns are equal. Then the next, we have a variable called total cost that is being set by default to infinity, and another variable called assignment, which is being set to null. The total cost, the minimum total cost, will hold the value, the smallest total cost in the solution, while the optimal assignment will hold the assignment sequence which has the smallest minimal total cost. Now, the next step, the first step in the next step in our algorithm will be to get the possible permutations of the different tasks with the different workers. After doing that, we have a loop, a for loop here, which we look over the different combinations or the different permutations to get their how to be assigned and their total cost. So the first instruction, we have our current cost, which is a variable which is being set to 0. And then we have another for loop which we look over, checking assigning each task to a person. And after doing that, after all the assignment, it takes the individual costs of each of those individual assignments and add it to the current cost. That is, we're incrementing the current cost. That is, for example, the beginning current cost was 0, so when we get the first assignment, we add it to that current cost, incrementing it to a new value. Then we check now if the current cost is less than the minimal cost. So for the first item or the first assignment, we check if the first assignment's total cost or current cost is less than the minimum total cost. And if this, then we assign it to be the current total cost, and then the optimal assignment will be that assignment. This is being done for every other permutation of the different tasks assigned to the workers or persons. Then after the optimal assignment has been found and the minimum total cost has been found, it is being outputted that this is the minimum total cost and this is the optimal assignment. Now let's demonstrate this further with an example. Now suppose we have this problem. We have n number of jobs with n number of different workers. To minimize the cost of work, we have a matrix M. Now in this our example, we are going to use mainly just 3 persons and therefore 3 jobs, and we have ji for the jobs that will be running from job 1 or j1 to jn. So our i's and j's that we'll be using here will be in the range from 1 to n, where our n is 3 because we have 3 jobs and 3 tasks. All right, this is how our matrix is going to look like. So if we say person 1 is being assigned job 1, the cost of that will be here, person 1, or person 2 if assigned job 2, for example, that cost will be here. Now let's put figures to this matrix. Now we have this matrix with figures that we want to look for the optimal assignment using the enumeration method. So as you can see, the number of rows equal to the number of columns in this matrix. Therefore, it's a square matrix. Our minimum total cost is infinity and our optimal assignment is null at the beginning. Following our algorithm, the next step is for us to come up with the possible permutations or different cases of assigning these different jobs to the 3 persons that we know. Now, in case 1 that we have here, P1 is being assigned J1, P2 assigned J2, and P3 assigned J3. Now, if we go back to this our matrix, P1 is being assigned 6 for J1, which is cost 6, P2 is being assigned J2, which costs us 8 units, and P3 is being assigned J3, which costs us 6 units. And if you come back to this our table, we have the 6 plus 8 plus 6 giving us 20. So here is our total cost, which is being assigned to our current cost. Now that current cost value is being compared with our minimum total cost. Now our mean total cost is having an initial value of infinity, meaning that this value overrides the initial value, meaning that our new minimum total cost is 20. Now moving to case 2, where P1 is being assigned J2, P2 is being assigned J1, and P3 J3. If we come back here, we look at this matrix following this assignment here, we have this sum of individual costs giving us 19. Now this new value is being compared with the current value of the mean total cost, and if it is lesser than that value, then it replaces the mean total cost. So 19 is lesser than 20, so it replaces the mean total cost. If it is not, it moves to the next permutation and continues this until the value of the total cost, which is lesser compared to all the others in the permutation, will be the mean total cost, and that combination assignment will be assigned as our optimal assignment. So in this case, 17 is lesser to all the other values in our combination or permutations. Therefore, this is our minimum total. This is our optimal assignment. We're having a minimum total cost of 17. As you can see, our minimum total cost is 17, and this is the optimal assignment. Next, we are going to look at the second method of solving an assignment problem. Hello, welcome back to the second part of this tutorial, where we are going to use the second method of solving assignment problem, which is the Hungarian method. Now, what is the Hungarian method? It is a method that is quite different from the enumeration method, which has a different approach in getting the optimal value. We will look at the different steps in solving assignment problems using this algorithm or method. But another name that you can find in books for this method is the Hofmann-Moncrief algorithm. And in this approach, we have two major types of problems that we can solve. We have the minimization and the maximization problems. With the maximization problem, we have a matrix, and in that matrix, the largest value from it, every other cost or value in the matrix is being subtracted from it to have a new matrix formed. Whereas in the minimization problem, we just start directly with the row and column reductions. Now, it has a time complexity of O to the n to the 3, where n is the number of jobs or workers. The following steps that we're going to look at will be followed to do or to compute the Hungarian method. The first step is to find the minimum value in each row and subtract that value from each value in the same row. Step 2, to find the minimum value in each column, subtract that value from each value in the same column. Step 3, we draw the minimum number of lines needed to cover all the zeros. And if those number of lines is equal to the number of rows that we have in our matrix, then we are done. We can now compute our optimal assignment. Otherwise, we move to step 4, where we find the smallest uncovered value and we subtract this value from all uncovered values and add it to the values at the intersection of lines. Then we repeat step 3 to get the minimum number of lines all over. Then we have step 5, where we circle the assignment from rows or columns with the minimum number of zeros, thereby finding the final total cost, which will correspond to the original table values, meaning that where we have the minimum zeros, it will assign those jobs to their workers or persons. Here we have the algorithm which we are going to use. There was the step, and this is the algorithm mathematical wise. Now I'm going to demonstrate this directly using an example. Now, using the same example we used as in our previous tutorial, we first of all check if the matrix we are using is an n by n matrix, that is a square matrix, and as you can see, the number of rows equal to the number of columns that we have in this matrix. So the next step in our algorithm is to get the minimum value in each row. Starting with row 1, the minimum value we have here is 5. So we'll get here 6 minus 5, here 9 minus 5, here 5 minus 5. The next row, the minimum value is 3. So we're going to have here 4 minus 3, here 8 minus 3, and here 3 minus 3. The next row, the minimum value is 5. So 5 minus 5, 11 minus 5, and 6 minus 5. Now, go ahead and do that computation and ensure that you have a matrix. Now, check the matrix that you have if it is equivalent to what you see on your screen. Now, we have this new matrix. We proceed with the next step in our algorithm, which is checking the minimum value column-wise. Now, starting with this first column, our minimum value is 0. So we will have any much difference because of 1 minus 0, 1 minus 0, and 0 minus 0. Nothing changes in this column. Moving to the next column, we have our minimum value being 4. So here we have 4 minus 4, 5 minus 4, and 6 minus 4. Coming to the next column, our minimum value is 0. So no change here also. So we have this. So go ahead and do the computations that I have mentioned and verify later on if it matches what we have. Now, you will realize that your new matrix will look like this. Now, the next step is for us to draw the minimum number of lines that will cover all the zeros in this matrix, meaning that we have a line that covers like this. For example, it covers all the zeros in this row. We need to cover this 0 here, and we need to cover this 0. We need to cover, I think that's all. Cover the 0 here, cover the 0 here, and cover this other 0. So there we have it. We have 3 lines that are covering all the zeros. Now we'll check if the number of lines are equal to the number of columns or rows that we have in our matrix. So we'll have 3 lines that have covered all the zeros that we have, meaning that the 3 lines equal to the number of rows. So we get our optimal assignment. Now this is the original matrix. So in the positions where we had the zeros, we look for the ones that have the minimum number of zeros, and that position will give us our optimal assignment for each of these persons to their jobs. Let's go back a little bit. So here we had, on this first row, we had 2 zeros. So I decide to use this first 0, meaning that we assign person 1 job 2. And then if we do that, block all of this and block all of this, meaning that we're not going to use this row and we're not going to use this column. Coming to person 2, the only 0 we have here is this, meaning that we assign person 2 job 3, and cancel like this, and this has already been cancelled like this. So move now to person 3. This is the only 0 we have here, so assign person 3 job 1, and this sequence will give us our optimal assignment. So the position of the zeros were 9, 3, and 5. Let's go back to confirm that. As you can see, position here where we had 9, position here that we had 3, and the position here that we had 5. So if you sum that up, it should give you our minimum total cost, which is 17 and we have our optimal assignment P1J1, P2J3, and P3J1. Thank you for being with us till this time. I hope you have a great understanding of what assignment problems are and the two algorithms that we've seen so far in solving assignment problems. See you next time.